Hello. The problem reads if a force of F equal to 350 newtons is applied to the handle of the toggle clamp, determine the resulting clamping force at A. Right. So we have this toggle clamp that is made out of a number of members. We have this one here, which is pin joined at B and C. We have the two force member itself, BE. Then we have this other member here joined at D and C. So basically, of course, and then we have the support itself, which is fixed down there. So we have one, two, three, four members. Okay. But of course, the ones that are going to help us this time around are just three. Okay, three members. So this problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So what we're going to do is we will have to draw free body diagram. We dismantle it first and identify the points that we can start with so that we do not waste so much time. So looking at this particular clamping device, uh, BE is a two force member, so it means there's only one axial force in there. Of course, it will have components in whichever axis that we choose. So BE is a two force member, and then so we only have a single force there, BE. And then we have point C. C will have components in the X and in the Y, and so is D. But we're interested to find the force at A. So for me, what I'll do is I'm going to draw the free body diagram for this outline I'm drawing right now in red. This one. Okay. Once I've done this, I'm going to take moments about C so that I find BE. And when I've found BE, I'm going to find the forces at C. And once I've found the forces at C, then I can come and take moments later on at D, this outline that I'm drawing in blue. I can come and take moments at D, and with this, I'll be able to find the reactions at A. Okay. All right. So let's do so. So to start with, let me draw the first case. Where can I draw it? Okay, I'll draw it on the other end there. So the system, something like this. Something like this. Okay, I may not draw it perfectly, and I don't need to draw it perfectly. All right. So something like this. So I have a force here, and this force is F, and we've been told this F is equal to 350 newtons, and it is 90 degrees to this system, to this handle. And then we have C here, and then we have B down there. I mean B here, somewhere there. Okay, so this is C, this is B. All right. So with this information, I'm saying at C there, let's say we are going to have two forces, CY and CX. And then here at B, let's assume, it doesn't matter which direction, assume whether in tension or compression. If it is wrong, it will correct itself. So if I looked at this, it looks as if it's in tension, compression. Okay, then let me assume that it is in tension. So if I did so, then I'll have an arrow going like this. Okay, this is my BE. And the angle for this one is already given. This angle here is given, this 30 degrees. This point here is 30. All right. And then we put the dimensions. We're going to have components. Let me indicate the components. This angle here is given also as 30. So I'll have a components. Let's say I'm going to have a component there of that force applied. Okay, this is 30. I'm going to have another component there like this. So this one is going to be equal to this angle here. If this is 30, therefore this angle is 30, right? So this is 30 degrees. So this one is going to be equal to 350 cos 30. Is that fine? Then this one it will be 350 sine 30. Great. Then we have other components here. Okay. Doesn't matter if this assumption is wrong. Okay. So let's say this, of course, like so, and then we have another one like that. So this is BE cos 30, right? Then this is BE sine 30. So let's add some more information. Dimensions. We have this dimension from here to there, from there to there. Dimensions. This is 70 millimeters, and then we have from here, where is this is 70, and then we have this line. Okay, this is 70, like so, and then this point here, we have this point. Let me just show that one. This is where this line, this is where this boundary passes. This boundary passes just there. Okay, this boundary passes just there like that. Let me draw it. This boundary passes just there like so. All right, so there we go. So this one here, from the point of the application of the force, this one here being told is 275. These are all in millimeters. These are all in millimeters. And then what else? Then we have this one from C to this one here. This one we've been told is what? This one is 30. Okay. This one is 30. This is 30 millimeters. What else? For now, I think this is enough. If I took moments here, I took moments at C, I have that component. I have. All right. So there we go. This is good. So let's take moments about C, and after we've done so, we are going to later on draw another free body diagram on the other side. So say summation of moments about point C equal to 0, and clockwise being our reference. So what do we have at C? What do we have at C? At C, we have the following. Minus 350 cos 30 times the lever arm here. The lever arm is going to be equal to 70 plus. I'm not converting these to millimeters because they'll cancel each other. I'm not converting them to meters. If you want to, you can as well convert them, but they'll cancel each other since we're going to be dividing. We just remain with newtons. So 70 plus this angle here. So we need to find this distance here, right? Okay. We need to find this distance. Okay, this distance here. All right. So to find that distance there, we have 30 there. Angle is 30, so that becomes 275 cos 30, right? And then we have minus 350 sine 30 times So this distance, we've already found this distance here. This distance, we called it, this one we called it 275 cos 30. This one is 275 sine 30, right? So that is 275 sine 30. All right. What else? We have BE and BE and BE, sine and cos. So we have a plus, a BE. Okay, BE sine 30 times the lever arm, which is 30 millimeters clockwise, and then we have minus BE cos 30 times 70, right, equal to 0. So let's find what BE is. Grab your calculator and do your calculation quickly. So minus 350 cos 30 70 plus 275 cos 30 close bracket minus 350 sine 30 275 sine 30 close brackets, and then divided by, we have sine 30 times times 30. So this one is 30 sine 30 minus 70 cos 30. All right, so there we go. We have a 2574. So this is going a minus. All right, minus 2574 0.881 newtons, right? 2574.81 newtons, right? So this is our BE. So we found what BE is, and with this information we can apply the summation of forces in the x direction, so that we find, and y direction, so that we find the component of Cx and Cy. So summation of forces, all right, let me come here. So summation of forces in the y direction equal to 0. So we have Cy up minus BE cos 30. Mind you, this negative just shows that the direction that we chose for BE, this direction, is supposed to be the other way around. Instead of it being in tension, it's in compression, okay? But for now, we are just going to use the values the way they are, okay? So BE, and then we have minus 350 cos 30 is equal to 0, right? Cy minus 350 and minus yeah, so let's find what Cy is. What is Cy? So Cy therefore is going to be equal to BE. We already know what it is. We just replace this value here. We replace it with a sign the way it is, okay, the negative sign, okay. So if we did so, then it's going to be equal to 257 sine cancels 2574.81 cos 30 minus 350 cos 30. All right, so we get a minus 1926.74 newtons. So that is what we get for the value of Cy. And then we have summation of forces in the x equal to 0. We have Cx plus 350 sine 30, and then we have plus BE sine 30 equal to 0. P again, we just replace it the way it is with this sign, and then we find the value of Cx. So Cx is going to be equal to, so let's find Cx. So it's 350 sine 30. BE is minus, so it's minus 2574.81 sine 30. So what we find is Cx is positive. It's 1112.405. Okay, newtons. Great. So now these signs, I'm going to change them on the other free body diagram I'm going to draw. So with this information, I'm going to draw this other free body diagram now, this part that I'm outlining in green, this one. Okay, since we found what C is, and that is what we're interested in, for us to find the reaction at A, we need to take moments about point D. So let's draw this quickly and replace all the values. So we have a system like this. We have a system like this. Okay. Okay. It may not look perfect, but it's going to be a representative of what I'm trying to drive home. So it is something like that. These points are in the same line. They are in the same line, the vertical direction. All right. So let's replace the values. This point is C, this is C, and this one is D. So CY we said is minus. Initially, look at this. We had written it like this. Okay. So ideally it's supposed to go down like this. Okay, because we found minus. So therefore here it will have to go up. Okay, it's important. This is very vital. Okay. And then Cx, we found it positive the way it is. It's okay the way it is. So here it is supposed to be going in this direction like that. Okay, so this is Cx, and we already found the answer. This is 1112.405, and Cy we said is 1926.1926.74. Then this dy, we are saying we have two components here, dy and dx. And then we have a mechanism here for clamping, okay, that I'm just going to indicate as well. Okay, a mechanism for clamping there. So we are applying a force down, therefore we expect a reaction coming up. Okay, this point is A. All right. So this one is our AY. Okay, this part, this plank here, this part here, this one is this part here. This part here, whatever we are clamping, whether it's a plank, is experiencing a force like this. This is AY. Okay, it's the same value AY. Okay, it's experiencing this. Okay, call them normal force or whatever, but it's experiencing this particular force. All right. So I think that's about it. We just put the dimensions. So from A to C, since A and C, since C and A are in the same line vertically, this horizontal direction, I mean distance, is 235 millimeters. And then this distance between C and D, the vertical, is 60. All right, 30 30 60. So this one is 60 millimeters. All right, so with this we can take moments about G. Like we said, vertically these are in the same line, so only the horizontal component will contribute. All right, so can we use this space here? I think so. We can use this space. This space is enough. Let me just put a demarcation here. I do like this. So this space in between is enough. So we are going to say summation of moments about point D. So we'll say summation of moments about point D equal to 0, anti-clockwise being our reference. So what we have a positive moment 112.405 times 60, okay, and then minus ay times 235, okay, equal to 0. So if we were to calculate that, we'll find that our ay is going to be equal to, what's our ay equal to? 112.405 times 60 divided by 235. So what we find is 284 point what? 0.02, right? Newtons. Okay, so the clamping force at this value here, okay, this value here, this one is equal to 284.02. All right, I think we are done. This is the final solution, ay. This is the final solution, the one I've just outlined in red. So, and I hope the video was helpful. If it was, give me a thumbs up, like my video, continue subscribing and sharing my videos. Bye bye, and see you in my next screencast.